Let's work through an example of how we might use these kinematic vectors. Suppose we're an air traffic controller and we need to keep track of two planes. So two planes are out there flying in the sky, and the worst thing that can happen is, of course, that they run into each other. So to do our job, we need to know where those planes are relative to us, and we also need to know how far apart those two planes are. So we need to know what the position vectors of our planes are, and also then the distance between them. Now, since we don't actually care what path the planes are following, we only care about the straight line distance between them, we can use our displacement vector to find out, because the magnitude of my displacement vector will tell me the distance between those two planes.
Now let's read through the problem and see if we can get a picture of what's happening in this problem that will help us answer these questions. As usual, and as I've said before, getting a picture and putting down a picture is the hardest part of any of these problems, usually. Often, once you have a good sense of what things look like, you have a pretty good idea of exactly how to go about solving the problem or finding the variables and values that you need to answer the questions. So let's see, there are two planes. There's the Boeing 747 and a Douglas DC-3. When talking about my variables, all of my B variables are going to be related to the Boeing, and all of my D variables, those will be for the Douglas. Reading through this problem, see, we have an air traffic controller monitoring the position of these aircrafts with respect to the control tower. That's the first thing I should keep in my mind. All of these values are measured as the air traffic controller sits in his control tower looking out at the planes. The Boeing, of course, is cruising at an altitude of 2,500 meters and climbing with making an angle of 10 degrees above the horizontal. And remember, that's with respect to the control tower. Then moving 30 degrees north of west. The Douglas, however, has an altitude of 3,000 meters, is making an angle of 5 degrees with the horizon, again with as measured by the control tower, and is cruising directly west. At this point, you should pause this video and answer the next quiz question. It's going to ask you, based on what you know of triangles and the height of the two planes and the angles they're making with the control tower, which of these two planes would we expect to be near the tower?
So you should have worked out that the Boeing ends up being closer to the control tower because it is lower in the sky but makes the larger angle relative to the horizon, whereas the Douglas ends up being higher in the sky but makes the shallower angle, and the only way that can happen is if the Douglas is further away. Now we've got a side view, but we're working in 3 dimensions, so we need an overhead view as well. So let's give ourselves some compass rose so we can tell where we are relative to the control tower. So there's the control tower in the center. We have a north, we have an east, we have a south, and we have a west. All right. We've got the Boeing here. This is the one in purple. And we've got the Douglas in blue. And we know that the Douglas is cruising directly west. So there's our Douglas. But our Boeing is cruising at an angle 30 degrees north of west. So there's the triangle, triangle for our Boeing. All right, now we've got our triangles. Now let's begin assigning variables. Well, actually, before we do that, let's pick our coordinate systems. I am going to choose up my altitude to be my positive y direction. I'm going to choose my north to be my positive z direction. And I'm going to choose east as my positive x direction. That way,
Now that I've got my positive directions chosen, now I know whether a vector component will be positive or negative. All right, the bowing, we said we knew what the angle was with respect to the horizon. That was 10 degrees. And we know what its altitude is. We also know what its angle is with respect to the west axis, right? So this x-axis, we said it was 30 degrees north of west. The Douglas, similarly, we know the angle that it makes with the horizon, and we know its altitude. All right. We also know it's cruising directly west. Now we have some choices. We can begin to label other quantities that we'll want. For example, we need to know what our x and z components are. We know what our y components are. Those are our altitudes. But we need x and z components. So for this bowing, this is my bowing, my x component is going to be that one, and my z component is going to be that distance. All right. For my Douglas, however, this now is going to be my x component for my Douglas. I already know, since I'm cruising directly west, I'm not north at all, that my Douglas will have a z component of 0. Looking at my side view, then, let's suppose I'm looking at my side view, I'm standing north, so I'm standing right here, and I'm looking south. If I look south, what I would get is this, then, is my x component. All right, and now my triangles are all assigned. My variables are all assigned. My triangles are complete. All I have to do is start using my trig. But before we do that, we should write down what we know and what we don't know, right? All right, so we know our altitude. That's 2,500 meters or 2.5 kilometers. We know what our angle is. That's 10 degrees. We know also what our angle is with respect to the compass rose. That was 30 degrees north of west. We don't know, and we want to know, what our x component is, and we want to know what our z component is. All right, that's for the Boeing. For the Douglas, we know our altitude. That was 3,000 meters or 3 kilometers. We also know what our altitude, what our angle is with respect to the horizon. That was 5 degrees. And we know our z component of our Douglas. That's going to be 0 kilometers. So for the Douglas, we're almost done. All we need to know for the Douglas is our x component. For the Boeing, though, we've got to work out what the x and the z components are. All right, now we've drawn our picture. Our picture gives us a pretty good idea of where everything is in relation to everything else. We've labeled everything we think we might need. We've written down what we know and what we don't know. And now we can begin to look for relationships, look at our definitions, look at our trigonometry, and see if we can solve things. At this point, you should be able to solve for the quantities we don't know, the components that we need to find our position. To help you out, I'll get you started. If we want to find out what our x component is for our Boeing, that's this one. We can look at this. We have a triangle here, right? This is our triangle. It is a right triangle. This is our opposite side for our theta b. Our x component ends up being our adjacent side, and so opposite and adjacent, that should suggest tangent. And I can write down this relationship. My tangent of my angle with respect to the horizon is equal to my altitude divided by my x component. By rearranging those, I get that the x component then is just my altitude divided by the tangent of my angle with respect to the horizon. And at this point, I'm going to let you go through and solve for the other two components that we need. We're going to need, go ahead and use your trigonometry and the values you've been given to find out what the z component for my Boeing is and what the x component for my Douglas is, so that we can then write out our position vector. One thing to remember that we chose east to be our positive direction. So our x components, we know that when we write this down, this xb, this is going to be negative. We're going to have to put in the minus sign so that this is really, to get the vector, this is really minus this value, this altitude divided by the tangent of the angle. Similarly, when you go to solve for xd, this is also going to be a negative value. So you'll have to put in that minus sign. So when you worked it out, you should have got vectors for your positions like this. Our Boeing has this vector on the top. As you can see, the values for the x components are negative. And for the Douglas, you should have received a vector or calculated a vector, something like this. Now, I have left off the implicit plus 0 k hat portion of it, just because. But if you don't like leaving that off, if that's going to confuse you, then by all means, keep your zeros. Now we want to find what our displacement is. So we now have our positions. We want to find how far away they are, and we said we were going to do that through the displacement. So we're going to find the displacement. Now, there are two ways of finding the displacement. We could find RB minus RD, so the position vector of our Boeing minus our Douglas. Or we could take these and flip them around, and we could find RD minus RB. Either of those are valid. They don't have the same meaning, right? The way we wrote it, this is moving from how we would have to move from the Douglas position to the Boeing position. That's what this displacement is telling us, how we would move from the Douglas to the Boeing. The other way is telling us how we would move from the Boeing to the Douglas. But it doesn't matter in the end, because ultimately we are going to be taking the absolute value of this whole thing. So we're going to just find the magnitude anyway, which will knock off the direction. All right, so if we put those together, we could write this quickly. The x component, that's just minus 14.1 minus 34.3 I hat plus 2.5 minus 3 j hat plus 8.2 minus 0 k hat. And when you work that out, you should get values of 20.2 I hat minus 0.5 j hat plus 8.2 k hat. That is my displacement vector. And again, that's my displacement from the Douglas to the Boeing, for moving from the Douglas to the Boeing. All right, there's my displacement vector. At this point, what I want now is I want to find out what is my distance will equal the magnitude of this vector.
And I'm going to let you figure that out.